let's look at a different example. The top and bottom margin of a poster are each 3 centimeters, and the side margin are each 2 centimeters. So we can draw a graph first. I know that I know the top and bottom margin, and I know the side margin. So let's draw like a rectangle. So let's say this is my poster, and top bottoms 3 centimeter margin, so maybe like this. Alright, and maybe the way I draw it doesn't look like it, so let me change it a little bit. Okay, and let me move to this side a bit. Okay, so let's say this is 3 centimeters. This is also 3 centimeters. And on the side is 2 centimeter. Here is also 2 centimeter. Okay, so that's the information I got from the first sentence. If the area of printed material on a poster is fixed at 90 centimeters square, which means the middle part, okay, this part is 90 centimeters square. Find the dimensions of the poster with the smallest area. Okay, dimension of the poster with the smallest area. So we are trying to minimize, right? Smallest, which means minimize. So we need to minimize area of the poster. Inside this part is printed area. So area of the poster, they are talking about this whole thing. Okay, so that's the question. We understand the question. We know what's given. We know what we need to minimize in this case. So now let's introduce variables. So I know this part is 90, and in order to calculate this area, well, at least I need to know those. So you can either set this to be a variable, this to be another variable, or you can do inside. It's up to you. Okay, it really is up to you. So what I'm gonna do is I'm gonna set this to be x and this to be y. In that case, this part, the the width of the poster itself will be x. So this is x. You have a 2 here, you have another 2 here, so that's gonna be x plus 4. And the side length here, this is y. You have 3 here, you have another 3 here, so this part will be y plus 6. Okay, so I have my graph labeled out as well. I have my variables, so let's define my variables properly. I'm gonna let x be the width of printed area, printed area, and y be the length of the printed area. Okay, not just that, because I'm trying to minimize this area. So let's give it a name. So let's call this A. Let A be the area of the poster. right? So now I know that I'm trying to minimize a. Okay, so if you look at before, we know that, well, I finished the whole 1, I finished the whole 2. Now I need to write a formula for this a. In this case, what I'm trying to minimize is a in terms of other variables. So my other variables, I have x, I have y, so I'm gonna write a as a function of x and y. Okay, that's my next step. So we know that the area a is basically x plus 4 times y plus 6. Alright, however, this has 2 variables, and as we mentioned before in this course, we only know how to deal with 1 variable, so we need to find the relationship between x and y. Okay, so as I mentioned here, if in step 3 the formula involves more than 1 variable, then we need to use the given info to relate those 2 variables. So x, y, you should have some relationship. Isolate one of them, plug it back into your formula for a, you'll get only 1 variable. So in this case, I know that this area is 90, and this 90 can be obtained by the product of x, y, right? So we also know that x times y is 90, which means my y is 90 over x, right? Then I can plug this back into this equation. So let's call it 1, call this 2, step 2 in 1. We would have a equals to x plus 4 times 90 over x plus 6. Let's open a bracket. You'll get 90 plus 6x plus 360 over x plus 24, which is 114 plus x plus 6x, and then plus 360 over x. Alright, so now we finished step 4. We have a formula of what we need to minimize here, and it's in terms of only 1 variable. So let me highlight this because this is what I know and I need to use it later. The next step is find the domain of this function. Okay, to find the domain, we need to, well, you know that the size of the poster either is this x or this y or this x plus 4 or y plus 4. They cannot be 0 and they cannot be negative, right? So that means both my x and my y has to be greater than 0. My x has to be greater than 0. My y is 90 over x has to be greater than 0, which would give you x has to be greater than 0 as well, right? So my domain is just x has to be greater than 0. That's my domain. Okay, so let me highlight it as well. Now we can try to minimize a. So let's take the derivative. We know that a prime exists within its domain, so don't need to check that. So just take the derivative and set it to 0. A prime is 6 minus 360 over x squared. Let's let it be 0. Then x squared equals to 60. And x is 2 root 15 or negative 2 root 15. And we know that x has to be greater than 0, so this one cannot be used. Let me move the whole thing. to this side a little bit more. Not in domain. Okay. No. Oops. Okay, whatever. Already smaller. Okay, that's better. Alright, so that means x equals to 2 root 15 is my only critical point. Alright, so now what we need to do is we need to either use first derivative test or second derivative test. Either one is okay. To check, to confirm that at this point, I'm actually gonna reach my absolute minimum. And you only need to check if this is a local minimum because, well, we don't have endpoints or anything, right? So in the last question, I used second derivative test. In this case, I'm going to use a first derivative test. So I'm going to draw like a table, let's say. So this is 0, and I don't want it to be 0. Till 2 square root of 15. This is where it is. And so on. And I have A prime and A. And let's check at those intervals. Is my A prime positive or negative? So now let's plug in, let's check between this interval. My A prime is a positive or negative. So when x equals to, let's say 1 is in between, right? So when x equals to 1, this is 360, so 6 minus 360 is obviously negative. When x is greater than 2 root 15, so you can try a really big number. Okay, try a really big number. You'll see that this part would be positive. Alright, and A prime is negative means that A itself will be decreasing, and this will be increasing. So at x equals to 2 root 15, this would give us a minimum value, a local minimum. Okay. However, as I mentioned before, we don't have any endpoints we don't need to check, and this is a unique local minimum, which made it the absolute local minimum. Okay, so by first derivative test, A reaches absolute minimum at x equals to 2 root 15. Why? Because we have a unique critical point. With no endpoint. Alright, so now let's go back and check if I actually answered the question. They asked me to find the dimensions of the poster, so I haven't answered the question yet because this x is this, okay? The dimension, I need to find x plus 4 and y plus 6. So I'm not really done yet. So let's first find y. Y from before, we know that it's 90 over x. So 90 over 2 root 15. That's gonna give me 3 root 15. Okay, so the dimension would be, y plus 6 and x plus 4. So the dimension of the poster will be 2 root 15 plus 4. Let's see what's a unit, centimeter, by 3 root 15 plus 6 centimeter. Okay, so that's this question.